Bam, Mr. Tarrou. Okay, in this video we're going to do 7 examples of converting equations back and forth between rectangular and polar form. So, we're going to use these 4 formulas that in my previous videos said, we can kind of come up with these on our own from our knowledge of trigonometry, but, they're given to us in the textbook. Let's use them to do these conversions. Let's start off with this question. R is equal to 5. Now, what form do you think that formula or that equation is in? Well, it has an R. Okay, remember, a point in a rectangular system is described as an x and y value, or an x and y coordinate, a left and right movement up and down. Polar coordinates use r and theta to describe points in a flat plane, and so thus, if you have an equation with r and theta in it, it's in polar form. In the first 5 examples, we're going to do 8 examples. In the first 5 examples, they're all going to be in polar form. We know that because they have r and theta in them. So here we have an equation, and the only thing that's fixed is the value of r. Well, what geometric shape do you know has only a fixed value of r, or a fixed radius, and every other measurement is fluid? That'd be a circle. So my guess is when we're done converting this equation, it's going to be just a circle with the point, the center, on the origin. So how do I get this equation with r and theta, or in this case just r, written so that it only has variables of x and y in them? Well, I'm going to use these formulas to try and do that that substitution back and forth between the 2 formats. And when I have only x's and y's left, I'm going to be in rectangular form. So I don't want to take r out and put in what? Let's see here. I could probably manipulate this and say that r is equal to sine theta over y. But I don't want to do a substitution that's going to introduce another polar variable in there. I want to just go, well, okay, r is the square root of x squared plus y squared, which is 5. And I'm either going to put these in sort of like a standard format or solve them for y in the rectangular format. So I'm going to square both sides and get x squared plus y squared is equal to 25. And indeed, that's what we're looking at here. We haven't studied conic sections yet, but when you have an equation with 2 squared terms, and those 2 squared terms have leading coefficients that are equal, and both of those squared terms have the same sign, then you're going to be looking at the equation of a circle. Now, I said a lot of concepts or characteristics there that we haven't studied yet in my class, and maybe you haven't either, but we have x squared plus y squared equals 25. So that's a circle with the center on the origin, and whose radius is equal to the square root of 25, or whose radius is equal to 5. Because remember, x squared plus y squared equals r squared. The equation of a circle is effectively just the same as your distance formula, which also looks very similar to your radius equation, again, just because the center is specifically on the origin. That's not the case all the time. It is the case, however, that the equation of a circle, if you've studied that yet, is very similar to the equation for distance, since the radius is a fixed distance. Okay, here we go. We have r is equal to 7 times the secant of theta. Let's rewrite that so that there's no r's and theta in it. Well, as I look at my conversion formulas over here, I don't see any conversion formulas with secant or cosecant or any other trig function for that, well, tangent, but there's no secant. So what I'm going to do is I'm going to take this equation and I'm going to write it like this. R equals 7 times 1 over cosine theta. Remember, secant and cosine are reciprocal functions. And I'm going to multiply both sides by the cosine of theta to get that division of cosine theta, or get that cosine out of the denominator. And we have r cosine theta equals 7. Now, that algebraic step has not put us into polar form, but it has given us, or has set us up for that substitution. R cosine theta is simply x. Now, don't forget, x equals a number is going to be the equation of a vertical line, even though it's the horizontal axis. And y equals a number is a horizontal line, even though, of course, it is the vertical axis on the rectangular coordinate system. Alrighty then, moving on. Third example, r equals 4 cosine theta plus 8 sine theta. Okay, again, r's and thetas, polar form. Let's get this into rectangular form and see what type of graph this equation would form. Because the graph is going to look the same whether you graph it in polar form. If you have a calculator, you can put that calculator in polar form and type this in. Or once we're done converting this into rectangular form, graph that, and it will be the same graph. Again, we are not looking at different shapes on two really different planes. It's still the same shape. We're just, again, describing different ways to get to those points. Anywho, r cosine theta is x. R sine theta is y, but we don't have r cosine. We have just cosine. We don't have just sine. We don't have r sine. We have just sine. So a direct substitution here is not going to be very successful or very handy, easy, convenient. So what I'm going to do is manipulate this equation a little bit before I do any kind of substitutions to go right into rectangular form. I'm going to take both sides of this equation and multiply both sides by r. Now there's two terms on the right. They're separated by addition and subtraction. So we're going to distribute that r and get r squared is 4 or equals 4r cosine theta plus 8 r sine theta. Now we have r equals square root of x squared plus y squared. So x squared plus y squared, I'm going to take that for r squared, just kind of squaring away the square root symbol, equals 4, and then r cosine theta is x plus 8 r sine theta is y. Now, we could call this a day and be done, but I'm going to give you a preview of what you're going to learn in the future. I'm going to give you a preview of conic sections and specifically just a circle, which you might have already studied. So this is going to be the equation of a circle, and I want to put it in standard form just to give you a review, if you've already studied circles, or give you a preview, my students a preview of what we're going to be learning later on in our textbook. I would like to know the equation of the circle in standard form. That means I'd like to know the center and the radius, the length of the radius. And I'm going to do that by getting all the x and y variables on the same side. So I'm going to write this as x squared minus 4x. And I'm going to leave some space for completing the square. I'm going to leave y squared here, plus y squared. Bringing the 8y over with subtraction. And again, I'm going to leave some space for completing the square, equals to 0. Now again, if you haven't studied conic sections, you can just fast forward this tape a little bit. If you have studied conic sections or studied circles or studied completing the square, you're going to know what I'm doing. And if not, you can kind of probably just skip it for now, depending on what you've covered in your book. You know, we all use different ones. I'm not sure what you've seen. So, I'm going to complete the square. Now, completing the square is when you take half of b. When you have quadratics in standard form, it's ax squared plus bx plus c, and that c is your constant. So b is in front of the single degree term. I'm going to take half of b, I'm going to square it, and add it to both sides. So negative 4 divided by 2 squared is 4, so I'm going to add 4 to both sides. Same thing with the 8. Negative 8 divided by 2 squared, this is called completing the square. That's going to be 4 squared, which is 16. And so I'm going to add 4 to the right, because I added it to the left. I'm going to add 16 to the right, again because I added it to the left, and clean this up. Now, when you complete the square, you create what is called a perfect square trinomial, which is a trinomial that is extremely easy to factor. It just follows a pattern. If you want to factor a perfect square trinomial, you square root the first term, you square root the last term, square root of 4 is 2, and you keep the middle sign. And therefore, x squared minus 4x plus 4 is literally just in factored form, x minus 2 times x minus 2. I'm writing it with a power of 2 because it has that fixed pattern. Plus Square root of y squared is y. Keep the sign of the middle term. Square root of 16 is 4. And so y squared minus 8y plus 16 is y minus 4 squared. And then 4 plus 16 is 20. Now we have the circle in standard form, and its center is at 2, 4, and its radius is the square root of 20, which is the square root of 4 times the square root of 5, and the square root of 4 is 2. So, double check my work here. Good. So we've got an equation in polar form, we've put it into rectangular form, and I did a little preview or review, depending on what you've covered in your book, of showing you that this is the equation of a circle, or at least this circle, in polar form, whose center is at 2, 4, and whose radius is 2 square root of 5. Bam! Alright, let's move on. Can't be missing any spots. Okay, our next example is going to be r equals 4 over 3 cosine x, or theta, plus sine theta. Well, what are we going to do here? Well, what I'm going to do is, I believe I'm going to multiply both sides of the equation by this entire denominator. I don't really like the fact that it's in the denominator. And there's a multitude of ways you can do this problem. But I'm going to get the trig functions out of the denominator by multiplying both sides of the equation by 3 cosine theta plus sine theta. And I'm a little tight on space here, so I'm just going to draw that. I'm going to put this to the left side and to the right side. If you see another way to do this problem, just fiddle with it and see how it comes out. This is how I'm going to work it. So we have r times 3 cosine theta plus sine theta equals, and now on the right hand side, because I'm multiplying by the entire denominator, I'm going to get those trig functions out of there and just be left with 4. Now I've got r times this binomial, which means that it is going to have to get distributed through the parentheses. And we get 3 cosine theta, whoops, forgot the r, 3r cosine theta plus r sine theta equals 4. Well, I've done a little bit of an algebraic manipulation, and now I've got that r cosine set up and the r sine that set up. So this is going to be 3x plus r sine is y equals 4. I'm going to subtract that 3x from both sides of the equation and get y is equal to negative 3x plus 4. Bam! Going from polar to rectangular. Okay. Moving on. Let's take a look at r equals 3 sine theta tangent theta. Okay, so what are we going to do here? Well, the first thing I'm going to do is, I don't really like to introduce square root symbols to both sides to an equation because then I have to get rid of it. And I've got sine, but if I had r sine theta, I could take it out and substitute it in with y, and we'll deal with the tangent here in a second. Now I only have one term on both sides of the equation, one on the left and one large one on the right. Remember, terms are separated by addition and subtraction. There is none, so this is one term. So when I multiply both sides of the equation by r, I'm going to get r squared. There's not multiple terms in here, so there's not going to be any distributive property. It's not 3r sine theta, r tangent theta. I'm not putting in 2 r's, I'm putting in just one, and this is, again, one term. So no distributive property. This is going to be equal to 3 I'm going to pair up the r with sine. Tangent theta. And look, r squared is x squared plus y squared. R sine theta is y. Now, tangent of theta. I got to get theta out. And I don't see a substitution in these two lines that I've been using for all my examples that will allow me to take out the tangent function and replace it with, oh, I can take out the tangent of theta and replace it with y over x. How convenient is that? So we're not always just using those r sine and r cosine formulas. This becomes 3y squared over x. And now, if for some reason I needed to make sure that it was in y in terms of x, in other words, the y values need to be alone, well, if I want to write this equation to only have one y value, then I got to get those two y terms on the same side. So I'm going to bring this y squared over, which is positive, I'm going to bring that over with subtraction and say x squared is equal to 3y squared over x minus y squared. Now, these two terms both have a y squared in them, which means I can factor that out. So we have x squared equals y squared times 3 minus 3 over x minus 1. And I want to get rid of this grouping that has two terms in it, but I'm going to just, for convenience sake, make those two terms equal to one term by finding a common denominator. So that's going to be 3 minus x over x. I'm going to take that 1 and make it x over x. So I have a common denominator. So now we've got x squared equals y squared times 3 minus x over x. And I want to get that y squared term, or that y squared factor alone. That y squared is multiplied by 3 minus x over x. If you want to get rid of a fraction, like if I said 2/3 x equals 10, you would multiply both sides by the reciprocal of the fraction. And that would be, you know, whatever I just said. So I'm going to take this fraction and multiply both sides by the reciprocal. And we have y squared equals x cubed over 3 minus x. Now, if you want that y in terms of x, you're going to have to square root both sides. And when you do your own square rooting, don't forget to introduce your plus or minus. Because, again, when you introduce your own square root, you know, what's square root of 16? 4, negative 4. You have to take into account both the positive and negative answer. If the textbook gives you the square root and it's positive up front, you only accept the positive answers. If there's a negative out front, you only accept the negative answers. If you do your own, you've got to take both of them. All right, bam, that was a pretty tough one. Now let's go the other way and attempt to write some equations that are in rectangular form in polar. So we have 2x minus y equals 4. I have x's and y's, so I'm in rectangular form. Get rid of them. Use these substitutions. We have 2r cosine theta minus y r, the y is coming out and r sine theta is going in its place. Both of those terms both have an r value or an r factor, so we're going to factor that r out. And to get r in terms of theta, divide everything by this big long parentheses. R equals 4 over 2 cosine theta minus sine theta. Bam! Okay, another couple of examples. This next one is going to be very, very quick. And this video is getting a little long, so you probably appreciate that. X squared plus y squared equals 36. Well, What does x squared plus y squared equal? Last time I checked, r squared. And the square root of both sides will give you r equals 6. I introduced my own square root there, and I just said when you introduce your own square root to take the positive and the negative answer. Why did I write only positive 6? Because we're talking about the radius of a circle, and you can't have a negative radius. I guess you could account for the negative radius, but you're still going to get the exact same circle anyway. So r equals 6. Alrighty then. Because in polar coordinates, your radius actually can be negative. You just move backwards. Okay, we got one more example. It's going to be a bit of a long one though. We have x minus 4 squared plus y plus 1 squared equals 17. And we're going to get this equation of a circle into polar form. Now I set up an example for myself before we started this video, and I made the numbers, I just made them up myself. Well, I made these up too, but I had to adjust them a little bit because the constants weren't canceling out very nicely, and it was very hard, or nearly impossible basically, to get it in terms of r in terms of theta, to get the r completely isolated. So if you have one of these equations in your textbook like mine, it's probably set up to work out relatively, well, as much as possible, relatively straightforward. No substitution is going to help us right now get r and theta in there very cleanly. So I'm going to expand this out and see what happens. If you take x minus 4, write it twice, and properly distribute it together, you will get a trinomial. It's going to be this answer, x squared minus 8x plus 16 plus y plus 1 squared. Again, y plus 1 times y plus 1. If you actually distribute that together and not try and shortcut it like so many students do, you will see that you get 3 terms, not just a common mistake what comes up with only 2. You'll see that I've used a set of parentheses around the second grouping. That's out of habit, just to make sure I don't use any sign errors, but there is just a plus sign in front of these parentheses, so they're really not going to do very much. We have x squared plus y squared minus 8x plus 2y. 16 and 17, or 16 and 1 makes 17. Now, it's been set up, to be honest, honestly with you, so that the constants will cancel out, so that ultimately I can get r in terms of theta, get r completely isolated. And I'm not sure in other textbooks if they're always going to work out that nice and neatly, but they do in my textbook. So hopefully you're finding the same in your books. If we subtract both sides by 17, that is going to be equal to 0. Now what do we have here? We've got, let's move these x and y values over. X squared plus y squared equals 8x when you add it to both sides of the equation, and negative 2y when it gets subtracted. And x squared plus y squared is equal to r squared. 8x, x is r cosine theta. Y is r sine. These two terms both have an r in them, so I'm going to factor that r out. And if I have 2 r's on the left and I have 1 r on the right as an entire factor, not just randomly sitting around somewhere, I can cross a couple of those out and have r is equal to 8 cosine theta minus 2 sine theta. I'm Mr. True. Hope those 8 examples help. Go do your homework. Woo! Bam!